Hey guys, we are starting a new chapter today. It's without saying that you're going to have to read the book. The pictures are pretty good on this one, and I'm not in front of you to show you all this stuff. It's a visual one, so bear with me. So let's go over section one. What is force? Force is a push or a pull that acts on an object. So a force is a push or a pull that acts on an object. A force can cause a resting object to move, or it can accelerate a moving object by changing the object's speed or direction. So, if I'm on the soccer field and a ball is just sitting here and I kick it, that's taking a resting object and making it move. If I am playing volleyball, I guess, and the ball is coming towards me and I tap it to keep it going or something, or if the soccer ball is already moving and then I kick it to make it go harder, that's accelerate a moving object by changing its object or its speed. Um, so it would also be baseball, like if the ball is coming towards me and then I hit it with a bat and it goes another direction, another speed, that would be another example of forces. Um, in the book, it's going to be a better object, but one way to measure force is a scale. Okay, and there's a picture in the book, and I don't know what page it is, but when you read it, it's a grocery store scale, and they're putting apples in it, and they're using force arrows. I don't know if it's already representing, so I'll go back over that. Okay, so units of force. Force is measured in newtons, and it's a capital N. So 1 Newton is the force that it causes 1 kilogram of mass to accelerate at a rate of 1 meter per second per second. So it's 1 kilogram times meters per second squared. Okay, so a Newton is equal to 1 kilogram times meters per second squared. So this right here, 1 Newton equals 1 kilogram times meters per second squared. The Newton is named after Sir Isaac Newton. He's the one the apple fell and he discovered gravity and all that, which apparently is not true, but whatever. Who explained how force, mass, and acceleration are related. So he's pretty cool. All right. So that is a new unit that you are going to have to know for this chapter. Normally in my classes, I pass out a note card. So, and then we put the unit and all the formulas on one note card. So right now you're kind of at the beginning. You have speed and you have acceleration. Okay, and now we're talking about force, which is a Newton equals 1 kilogram times meters per second squared. So maybe get a piece of paper and just keep all of these formulas and units together because it's going to get more confusing. Okay. Representing force. So going back to the picture, and it says it's on page 357, figure 2, right here. It says the arrows are used to represent the direction and the strength of the force. So I'm not looking at it, but I've taught this quite a few times out of this book, and it's like apples. And they have one picture of an apple with a scale, and one picture of an apple with a scale. And they have a certain many apples, and the arrow is pointing down because the force is going down because the apples are in it, and so it's pushing the scale down. And then the other scale is doing the same thing. The apples are pushing it down. But you'll see that one has more apples than the other one. So the force is longer and thicker. Okay, so that shows you the amount of force. So the one with more apples is going to be thicker and longer, maybe. And then the one with less is going to be shorter and maybe thinner. I can't remember exactly. I'm having to do this from memory. Okay, but you can use arrows to represent the direction and the strength of the force. The direction of the arrow shows the direction of the force. So that's why on the scale it's pushing down. Okay. Okay. So combining forces. If you combine force arrows to show the result of how forces combine, or you can combine force arrows to show the force. And again, I usually use a desk or something like that to show you this, but you're just going to have to imagine. But there are pictures in the book, and it's really good. So forces in the same direction add together, and forces in the opposite direction subtract from one another. So imagine this, okay? in the back of my room, there's that big cabinet desk. I call it a desk, okay? It's like Miss Lafferty's, how she has that big one in the front. I used to have the other room that had the big one in the front. But let's pretend it's in the back, okay? If me and another kid, let's say Rossi, okay? If we're both pushing at one end and we're pushing the same direction, and let's pretend that the actual cabinet can move, okay? It's actually nailed down because it has pipes and stuff in it and it has plugs. But let's pretend that it can actually move. If we are both pushing on that end on the same end, going towards the left, let's say, his force and my force add together in the same direction because we're pushing, going the same direction. Okay. Now, opposite directions. Let's pretend that I'm on one side, he's on the other. I'm pushing to go forward, and he's pushing to go forward because he's going towards me, and I'm trying to push it towards him. Those subtract. Okay, and there's pictures of this in the book, and I don't remember what those pictures are, but I'm guessing it's probably after 357. All right, the net force is the overall force acting on an object after all the forces are combined. So if we're both pushing on one end and we're pushing in the same direction, we're going to add my force and his force, okay? If we are opposite to each other, so like he's pushing towards me and I'm pushing towards him, let's say that Rossi is pushing with 50 newtons and I'm pushing with 100 newtons, okay? Because I'm obviously stronger. So we're going to subtract that. So the net force is 50 newtons. Okay. Now, if he's pushing with 50 newtons and I'm pushing with 50 newtons, the net force is 0. Okay. Balance forces. So when the forces on an object are balanced, the net force is 0 and there is no change in the object's motion. So this is an example of tug of war or arm wrestling. So let's say it's arm wrestling and let's say it's sophomores versus seniors, I think it is. The sophomores are pushing one way, the juniors are pushing the other way, and I mean the seniors, and no one's moving. That like the rope's not moving, net force 0. And no one's moving. Okay? Arm wrestling. If you're arm wrestling somebody, like me and Rossi again, and we're both arm wrestling and our arm is not moving, it's because we're using the same amount of force. Okay? Now, when I, Hulk it out and I end up like crushing him, then the net force will be higher because, I have more force than Rossi. Sorry, Rossi, I had to. All right. So just know that if they're balanced forces, there's no movement. Okay? Unbalanced forces, this is where an unbalanced force is a force that results when the net force acting on the object is not equal to 0. So let's pretend we're back at that cabinet in the back of my room. I'm pushing with 100 newtons of force. Rossi's pushing with 50 newtons of force. Because it's not balanced, it's going to push, because I have more force, the cabinet's going to go towards Rossi because I'm pushing with more force. Okay? That's what an unbalanced force is. So when an unbalanced force acts on an object, the object accelerates, which means moves. Accelerates means moves. Okay? And the example on this is 358, figure 4. Okay? So there's a lot of pictures on this. Please go over those. I'm going to stop right here and let y'all look at all the things and read up until friction. Okay? And then we'll talk tomorrow. Or actually, this is Sunday night, so we'll talk Tuesday.